Hello, how are you? Today I want to finish the local search techniques. Remember, so far we've had hill climbing and the simulated annealing. Now I'd like to try the third of them, the genetic algorithm. So this is an algorithm that I think is a little more understandable than the simulated annealing. It's based on the idea of taking a population of possible answers, of states of your problem, and then mating two of those to get another state, and to try to do it by the same kind of biological mating, where, as far as we can tell, genes are picked randomly from either the father or the mother. And also, they throw in genetic algorithms mutations of certain genes. Now, I think the best way to understand this is to talk about it as an example. What I'm going to try to do is do the n queens problem in pieces. This part today will be just the beginning of it, but I'll give you the whole algorithm and see what we can do. So here's the way I look at the algorithm. First, we create an initial population of states of our problem. So whatever we somehow produce them, probably randomly. Next, we evaluate each of the states. Our evaluation you've actually already seen for the n queens. It was in homework 2. We'll use the same one here. That one, low score 1, so we'll have to sort of play with it a little to make sure that we pick the best of the items in here. So once we get that done, we repeat the following. Generate a new generation by mating to any two different members of the previous generation. That's not too hard, but there's a little bit of a quirk in here. We choose the parents randomly, but the best solutions are chosen more than the others. This is the famous survival of the fittest that evolution has in it. We may also throw in some random mutations. Now we have a new generation. Our object is to try to fix it, to look and see if we've found our answer. Maybe we have. If we have, we're done. If not, we keep going. So we repeat this until we reach an acceptable state in the generation. But once we get something we like, we're done. Now, that's all well and to say that, but there's a lot of things about how do you implement that. So I'm going to bring in a few things right now that I've been playing with and see how you feel about them. Here's what I'm going to bring in. This is your homework. This is what is going to be your homework. I'll be putting it out in a minute so you can see it. It's the first part of your homework, I should say. It'll be a homework on its own, but there may be other pieces using it. We're going to look at a genetic algorithm to solve the n-queens problem. Now, I've been looking on the web to find good solutions and methods, and this one, I've taken some ideas from there, many ideas from there, and I've written some of these pieces already. So let's look. We have the n-queens. Remember, that is, we want to put n queens on a chessboard that is n by n in such a way that no queen is on the same row, the same column, or the same diagonals as another queen. Now, this is an interesting representation. This I have taken from the web. Well, say we have n is 8. Then our representation, that should be if, it's okay. Our representation will be a vector of 8 places, an array of 8 places. Each of these places represents a column. So we'll have, let me pull this up a little. When we have 1 here, that means that in column 0, our queen is in the 1 row. In column 1, our queen is in the 3 row. Remember, 0, 1, 2, 3. In column 3, our queen is in the 0 row, and so on and so on and so on. Now, this means that we don't have to worry about queens being in the same column. All our results will be queens in different columns. That makes it a little easier. So, I want you to write a program that contains a constant int n so that we can vary from 4 queens to 6 queens or whatever we feel like. You're going to ask the user to input a position. And then you're going to evaluate the position and print out the position. The evaluation will be the number of pairs of queens which can take one another, if there were no intervening queens. This is the same thing you use on homework 2. And here's an example. Here's a 4 by 4. Queen 1 can take queen 3. So there's 1 pair. Queen 2 can take queen 4 and queen 3. So there's a 2nd pair. Queen 3 can take queen 4. Now you'll notice I do not have 3 to 1 and 3 to 2 because I'm only looking at pairs. I'm not double counting. So the easiest way is to just go down. Look at the ones with 1 in them, then the ones with 2 in them, then the ones with 3 in them, and the ones with 4 in them. Or in this case, look at the columns 1 by 1. Now you can see there's the output of my program for 1 run. I am having a cat cry in the background. I'm sorry if that bothers you, but she's always thinking she should get more food. She must have caught it from me. it's pretty easy to figure out how you check if they're on the same row. After all, if 1 and 1 are the same, then they obviously, this one can take that one. So that's not too hard to do. But figuring out if they're on the same diagonal can be a little more complicated. I suggest you look at the row and column and take a diagonal and look at row, column, row, column, row, column, and row, column of that diagonal. And see if you can get a relationship where they all have the same sum of the row and column, or the difference of the row and column, or whatever. Remember, you have 2 diagonals to look at. One going from northwest to southeast, and one going from northeast to southwest. So I'd like you to try that. And as I've said, there's an example of my output. So hopefully you can come up with the same kind of thing. I'll be putting out this homework and that genetic algorithm outline I wrote in a few minutes. And I hope that you have a great weekend. I realize that many of you are shut in, but it's sad. We hope it's over soon. The president's letter only extended it a week, so maybe in a week's time we won't have this problem. So I'll see you later. Bye now.